A bridge is more than just a structure, it's a bold statement of human confidence. It represents our ambition to connect, to overcome, and to push the boundaries of what's possible. It's an act of faith, a testament to our belief that we can span a seemingly insurmountable void and defy nature's imposing barriers. These structures symbolize our ability to engineer solutions that bring us closer together. We place our trust in the strength of steel and the solidity of concrete, the very materials that form the backbone of these monumental achievements. But the earth holds secrets, and earthquakes attack from below, a hidden menace lurking beneath our feet. They shake the very ground we rely on, the stable foundation upon which we build our dreams and our infrastructure. The Earth's raw power becomes a direct threat to our carefully constructed world. Unlike the predictable forces of wind or rain, which bridges are designed to withstand, seismic waves send powerful shock waves rumbling through the earth, an invisible force tearing through the ground. This subterranean assault turns a bridge's own massive inertia, its resistance to movement, into its greatest enemy, amplifying the destructive forces. The foundations are violently yanked in one direction, while the heavy deck, resisting the sudden motion, stubbornly tries to stay put. This creates immense stresses, internal conflicts within the structure, threatening to tear the entire bridge apart at its seams. The challenge for engineers, therefore, is not just to build for brute strength and unwavering rigidity, but to create bridges that possess the ability to flex and move with the Earth's tremors, absorbing the earthquake's energy, dissipating its power before it can cause catastrophic damage. The key is not resisting the force, which is often futile, but accommodating it. The story of earthquake-resistant bridges is a testament to human ingenuity, about learning to dance gracefully with the shaking ground, adapting to its rhythm. It's about more than just standing firm. It's about resilience, adaptability, and understanding the forces of nature. For decades, bridges were built to be rigid, immovable monuments to strength, but earthquakes don't deliver steady pressure, they unleash rapid, unpredictable vibrations. Rigid bridges transmit this energy directly, often leading to catastrophic failure. The breakthrough came when engineers embraced flexibility. Bridges that bend and sway can dissipate seismic energy safely. Modern designs use ductile materials and built-in fuses that yield in a controlled way, protecting the structure as a whole. The goal is no longer to resist every force but to ride out the earthquake and remain standing. Flexibility, not brute strength, is now the key to survival. Earthquake-resistant bridges represent a remarkable feat of engineering. They stand as testaments to our ability to design structures that can withstand some of nature's most destructive forces. These bridges rely on ingenious devices, carefully integrated into their design. These aren't just afterthoughts, they're fundamental to the bridge's ability to survive a seismic event. These devices are designed to manage movement, specifically the intense and unpredictable motions caused by earthquakes. They allow the bridge to respond dynamically. Base isolators, layers of rubber and steel, are a key component. These layers are meticulously designed and manufactured to provide specific levels of flexibility and strength. They separate the bridge deck from the shaking ground, acting as a buffer between the Earth's movement and the structure above. This separation allows the isolators to absorb horizontal motion, preventing it from transferring directly into the bridge's superstructure. Dampers, like giant shock absorbers, work in conjunction with the isolators. They convert the bridge's swaying energy into heat, dissipating the force of the earthquake. This process is crucial for slowing dangerous oscillations, preventing the bridge from resonating and potentially collapsing. Sliding bearings, such as friction pendulum bearings, offer another layer of protection. They let the deck glide gently, allowing for controlled movement during seismic activity. This gliding action stretches out vibrations, reducing their intensity and impact on the bridge's structure. By doing so, they keep the bridge in sync with safer frequencies, minimizing the risk of catastrophic failure. Together, these systems, isolators, dampers, and bearings, transform violent shaking into manageable motion, protecting the bridge and its users. They're the hidden heroes, working silently and effectively beneath the surface. They are what allowing bridges to move with the earth, flexing and adapting to the seismic forces. This approach is far more effective than resisting the Earth's power. It's about working rather than against it. This choreography of flexibility and control, this delicate balance between movement and stability, is what keeps modern bridges standing, even when the ground beneath them is shifting violently. It's the reason these structures can remain operational and safe after the ground stops moving, providing vital transportation links. It's a triumph of engineering over chaos. A testament to human ingenuity in the face of natural disaster. Devices matter, but so do the materials themselves. Reinforced concrete with embedded steel rebar, combines compressive and tensile strength, allowing columns to bend without breaking. Modern steel is engineered for ductility, stretching rather than snapping under extreme stress. Engineers design certain steel elements to yield in a controlled way, absorbing seismic energy and protecting the bridge. Advanced composites like fiber-reinforced polymers, FRPs, are now used to wrap columns, boosting strength and preventing explosive failures. These lightweight materials also reduce the bridge's mass, lessening the forces it must endure. The right materials, used wisely, are as crucial as any device in earthquake survival. The Golden Gate Bridge, a majestic span connecting San Francisco to Marin County, stands as an iconic symbol of American ingenuity and architectural prowess. Its vibrant orange hue, often veiled in mist, has captivated imaginations for generations. But beyond its aesthetic appeal, this bridge is located in an earthquake-prone San Francisco, a region known for its seismic activity and the ever-present threat of powerful tremors. The region's history is punctuated by devastating earthquakes, making structural resilience a paramount concern. Recognizing this vulnerability, the Golden Gate Bridge underwent a massive retrofit after the devastating 1989 Loma Prieta quake. This seismic upgrade was not merely a repair job, it was a comprehensive overhaul designed to ensure the bridge's survival in future seismic events. Engineers embarked on a complex and ambitious project, reinforcing the bridge's towering structures, the very backbone of its suspension system. These towers needed to be strengthened to withstand the immense forces unleashed during an earthquake. They also deepened the foundations, anchoring the bridge more securely to the bedrock below. This involved extensive excavation and the installation of robust support systems, ensuring that the bridge's base could withstand ground movement. And, crucially, they installed giant dampers, sophisticated energy-absorbing devices designed to mitigate the impact of seismic waves. These dampers act like shock absorbers, dissipating energy and reducing stress on the bridge's structure. All of this enabling the bridge to survive a far stronger quake than it was originally built for, a testament to the power of modern engineering and proactive risk management. The upgrades transformed the Golden Gate Bridge into a symbol of resilience. Across the Pacific, Japan's Akashi Kaikyō Bridge, another marvel of engineering, faces its own unique set of challenges. Spanning the turbulent Akashi Strait, this bridge is not only one of the longest suspension bridges in the world, but also one of the most resilient. The Akashi Kaikyō Bridge was still under construction when the devastating 1995 Hanshin earthquake struck directly beneath it, a terrifying test of its structural integrity. The earthquake served as a harsh reminder of the unpredictable forces of nature. Incredibly, the towers shifted nearly a meter apart during the quake, a dramatic demonstration of the forces at play. This displacement highlighted the importance of flexibility and adaptability in bridge design, but the bridge survived, a testament to the innovative use of ductile steel, a material that can deform without fracturing, absorbing energy, and preventing catastrophic failure. The bridge also incorporated advanced dampers, sophisticated systems designed to dissipate seismic energy and minimize stress on the structure. These dampers played a crucial role in mitigating the earthquake's impact, and fundamentally, a flexible design allowed the bridge to move and adapt to the earthquake's forces, preventing it from collapsing under the strain. This flexibility is a key element of its resilience. Both bridges now stand as proof that with the right engineering, careful planning, and innovative materials, even the most violent seismic forces can be conquered, transforming potential disasters into triumphs of human ingenuity. These projects blend heritage and innovation seamlessly, demonstrating how the lessons of the past can inform the engineering solutions of the future. They are shining examples of how old and new can work together to create structures that are not only aesthetically pleasing, but also incredibly resilient, safeguarding lives and infrastructure. They're not just feats of construction, they're profound lessons in adaptation, demonstrating our ability to learn from nature's challenges and build a more resilient world. The world's great bridges are now built to endure the test of time and the forces of nature, not just to impress with their grandeur and scale. They stand as symbols of our commitment to safety and resilience. Tragedy has been engineering's greatest teacher. The 1971 San Fernando earthquake revealed that weak rebar and poor column design led to catastrophic collapses. This spurred new codes, Columns must now be ductile, with dense spiral reinforcement to confine concrete and prevent sudden failure. The 1994 Northridge quake exposed another flaw: bridge decks unseating from their supports. Engineers responded by widening seats and adding steel restrainers, ensuring decks stay anchored during violent shaking. Each disaster rewrote the rules, making bridges safer for the future. Failures are painful, but they drive progress. Every lesson learned in rubble has saved lives since. Thousands of older bridges still need protection. Enter seismic retrofitting. Engineers wrap columns in steel or composite jackets, strengthen foundations, and anchor structures deep into bedrock. These upgrades prevent collapse from soil liquefaction and violent shaking, extending the life of vital infrastructure. Before building or retrofitting, engineers use computer simulations and shake tables to test designs against virtual and real earthquakes. Digital models reveal weak points. Shake tables validate solutions in the real world. This cycle of simulation and testing ensures new and old bridges alike can withstand the Earth's fury. Through innovation and adaptation, our bridges remain symbols of connection, not catastrophe.